Welcome to the deep dive. Today we're tackling a really fundamental concept in computer science, the stack data structure.
Yeah, it's a cornerstone, really.
Absolutely.
Yeah.
And I think a good way to picture it is like you've got a stack of books, right, on your desk.
hmm
The only one you can really grab or add a new one to is the one right on top.
That's a perfect analogy. It really captures it. At its heart, a stack is, well, linear. Items are in a line.
Okay.
But the key thing, the rule, is you can only touch the last item added, the one that's, sitting right at the top.
Like a Pizzy dispenser. I remember those.
Exactly like that. Candy only goes in and out the top.
And that gets us to this core idea, LIFO, right? Last in, first out.
Precisely. Think about stacking plates. You put a clean one on top.
And that's the first one you grab next time. Yeah.
That's the defining behavior. Last one in is the first one out.
So it's not just like a physical pile, but a concept, an idea for managing data.
Exactly. We call it an abstract data type, or ADT, which sounds fancy, but it just means we're focusing on what you can do with it first.
Right. The operations.
Yeah.
Not worrying so much about like how the computer actually stores it in memory just yet.
Yeah, we'll get to implementation, but the concept comes first. What can it do?
Okay, so what can it do? What are the main actions?
Well, there are really two fundamental ones. First is push data.
Push, okay, like pushing a book onto the stack.
Exactly. You're adding a new piece of data onto the very top. It becomes the new top item.
We've got some visuals here that show it well. You see the stack, then boom, a new item appears right on top.
Yep, pushes everything else down effectively. It's always added at the top.
Okay, makes sense. And the second main one,
That's pop. It's the opposite.
taking the top one off.
Exactly. It removes the last item that was added, the one currently at the top. That item's gone, and the one underneath, if there is one, becomes the new top.
And the visuals show that too, top item just vanishes and the stack shrinks. Sort of.
Right. Those are the core two. Push and pop. Adding and removing from the top.
But you mentioned there are other operations too, secondary ones.
Yeah, there are some others that are really useful for getting information about the stack without, actually changing it.
The look but don't touch operations. Okay, what are those?
Well, first there's top, sometimes called peek.
Top. So that just looks at the top item.
Precisely. It tells you what the last item pushed was, the one currently accessible, but it doesn't remove it. The stack stays exactly the same.
Okay, handy for just checking what's next. Then there's size. That sounds straightforward.
It is. Size. Just returns the total number of items currently in the stack. How many books are in your pile right now?
Simple enough. And is empty.
That's a yes-no question for the stack. Is it empty? It returns true if there's nothing in it, false otherwise.
Got it. Like checking if the Pez dispenser is empty before you try to get one.
Exactly. And the last one is full.
Is full. So this implies stacks can have a limit.
They often do, especially when implemented with certain structures like arrays. So is full returns true if the stack has reached its maximum capacity and you can't push anything else onto it. Otherwise, it returns false.
Okay, like a full suitcase. No more room.
Right. So push, pop, top size is empty, is full. Those are the main operations.
Let's maybe walk through a quick example to see them in action.
Good idea. Let's start with an empty stack. Imagine it's empty.
Okay, empty stack.
First, we push. What's the state?
The stack now just has one in it and one is at the top.
Perfect. Now we push 2.
Okay, now 2 is on top and 1 is underneath it.
Right. One more. Push 3.
So 3 is the new top, then 2, then 1 at the bottom. Stack has 3 items.
Excellent. Now let's use pop.
Pop. Okay, that removes the top one, which is 3. So we're left with 2 on top and 1 below it.
Exactly. The stack now has size 2. And finally, let's ask is full. Assuming our stack could hold, say, 5 items.
Well, I only have 2 items now, so ends full would definitely be false. Still got room.
Perfect. See how those operations manipulate and describe the stack.
Yeah, that makes it much clearer. Now, I heard you can use stacks for something kind of cool, like reversing a sequence of things.
Ah, yes. It's a very neat and common application. The LIFO principle makes it work perfectly.
How does that work? Let's say we have the sequence monocle 1.5, 2.3, 6.7.
Okay. Take an empty stack. First, push 1.5.
Okay, my negative 1.5 is in.
Now push 2.3 is now on top of negative 1.5.
And finally push 6.7.
So 6.7 is the topmost element. Below it is 2.3, and at the bottom is -1.5.
Right. Now, what happens if we start popping?
Well, the first pop would give us the top element, which is 6.7,
Yep. And the next pop.
that would give us 2.3.
And the final pop.
Just as magical 1.5. Hey, look at that. 6.7, 2.3, negative 1.5. It's the original sequence completely reversed.
Exactly. Because the last thing you put in, 6.7, was the first thing to come out. It naturally reverses the order. Simple, but powerful.
That is really clever. Okay, so as we get deeper, there are a few specific terms we should probably know, right? Yes, a few pieces of terminology are helpful. We've used top conceptually, but in an actual implementation.
Right. How the computer handles it.
Yeah. Top often refers to a specific pointer or an index variable. It's the thing that keeps track of where the topmost element actually is in the memory structure, whether that's a list or an array.
Okay, so it's like a marker pointing to the active end of the stack.
Precisely. Then there are the error conditions we need to be aware of.
Right. Things going wrong. We mentioned is
Yep.
filled.
Related to that is stack overflow. That's the error you get when you try to push an item onto a stack that's already full. There's no space left.
Overflow, like a cup overflowing. Makes sense. And the opposite.
The opposite is stack underflow. This happens if you try to pop an item from a stack that is already empty.
Ah, trying to take something out when there's nothing there.
Exactly. Can't pop from an empty stack. So overflow on push to full, underflow on pop from empty.
Got it. And you mentioned implementations. Often in code, this would be bundled up, right? Like in a class.
Yeah, typically you define a stack class. It would contain the actual storage, maybe an array or a list. And that top marker we talked about, often called my top or something similar.
And it would have the methods for the operations.
Absolutely. It would need a constructor to set things up initially, and then methods for is empty, push, pop, top, maybe size, and he's all full too. It bundles the data and the operations together.
Okay. Now, stacks seem simple, but you hinted they're used everywhere. What are some big real-world examples?
Oh, tons. We saw reversing things. They're crucial for evaluating mathematical expressions, which is a whole topic in itself.
Right.
But think about your web browser's back button. How does it know where to go back to?
It remembers the pages I visited in order.
Exactly. In reverse order, really. When you visit a new page, its address is pushed onto a stack. When you hit back, the address is popped off and the browser navigates there.
Last page visited is the first one you go back to. LIFO. That's brilliant.
It fits perfectly. Another huge one is the undo functionality in text editors or other software.
Ah, yeah, crudo plus Z. How does that work?
Very similar. Every action you take, typing, deleting, formatting, gets pushed onto an undo stack, maybe storing information about how to reverse the action. When you hit undo,
It pops the last action and reverses it.
you got it. Stacks are also fundamental for backtracking algorithms.
Backtracking. What's that used for?
Think about solving a maze. You go down a path, hit a dead end. You need to go back to the last place you made a choice and try a different way.
Okay.
Stacks are perfect for remembering those decision points, those paths taken. You push your current position before exploring. If you hit a wall, you pop your last position to backtrack and try another path. It's used in games, pathfinding, solving puzzles.
Wow, okay. That's quite a range. And you mentioned memory management and function calls too.
Yes, this is absolutely critical in programming. How does a program keep track of function calls, especially when one function calls another, which calls another?
Nested calls, right?
Right, nested calls, exactly. And how does it know where to return to when a function finishes? And what about the variables inside each function? It all relies on a stack, usually called the call stack or runtime stack.
Okay, so stacks are doing a lot behind the scenes. How do we actually build one? Let's talk about the array implementation.
Right. Since a stack is linear, an array seems like a natural